Alright, so this is section 11.9 and it focuses around what's called normal distribution. This is the last section that we're going to be covering in chapter 11. It's probably one of the harder ones. Like most of the sections that we've done for this test haven't been all that difficult. This one's going to be a little more difficult just because it's going to focus around interpreting graphs. So what it says here is it says, many common statistics such as human height, weight, or blood pressure, when we gather a bunch of samples from the natural world, they tend to form a normal distribution. So we're going to get lots and lots of samples, and we're going to plot them all on a graph, and then they'll have what's called a normal distribution. And what that is it's data that varies randomly from the mean. So our mean value, our average value, they vary randomly around that value, and they form a mound-shaped pattern that is symmetric about the mean. So a normal curve is obtained by drawing a curve through the midpoints of the tops of the bars of a histogram of normally distributed data. So what that's saying is if we took all that data that, say we were gathering information about heights, and we were getting a bunch of different heights, and we graphed all that in a histogram, what you would do is at the midpoints of your bars on your histogram, you would draw a curve, and it would end up looking something like you see over here on the right. A normal curve is also the graph of a normal distribution. So when you graph a normal distribution, you should get this curve, which is called the normal curve, or sometimes it's referred to as a bell curve. It has a bunch of different names. And then the standard normal curve is a normal curve with a mean of 0. So your mean value would be 0, and your standard deviation is going to be 1. So for each standard deviation, you move 1 unit. So this on the left is actually the standard normal curve. Our mean right in the middle is at 0, and then to the left and right, we add and subtract 1 to get that standard deviation, 2 for the second, and 3 for the third. So then there are some properties that we need to know about normal distributions. And this graph we're going to get very familiar with. So make sure that you know how to interpret that graph. So some properties for normal distributions are that the curve is symmetric about the mean. So we have our mean in the middle. On the left-hand side and the right-hand side is the same. That's what symmetric about the mean means. The total area under our curve is 1. The mean, median, and mode are about equal. About 68% of the area is within that first standard deviation. So remember when we were talking about standard deviations, that one standard deviation is 1 to the left and 1 to the right. So this is our first standard deviation. 68% of your area is within that part of the graph. If we expand out to the second standard deviation, so that's from this deviation to this deviation, because remember, a standard deviation is on both sides of the mean. That is 95% of your area. And then if we go as far as to include the third standard deviation, that's 99% of your area. So within 3 standard deviations, we have 99% of our area. So there is still a little area past the third deviations. It continues on just a little bit. There's like that 1%. So now we're going to actually look at some examples where we're going to use the normal distribution to solve some problems. So in example 1, it says that the bar graph gives the weights of a population of female brown bears. The curve shows how the weights are normally distributed about the mean. Your mean is 115 kilograms, and the standard deviation is 10 kilograms. And then part A says, approximately what percent of female brown bears weigh between 100 and 129 kilograms? So what this type of problem, when you're given a graph that it has the histogram part to it, which is your bar graph, and you're told these are your weights for the brown bears, and they're given in intervals. So this is like 80 to 89, 90 to 99 for each bar. They're given in a range. And then your other axis is the percent of brown bears that weigh in that interval. So for part A, we want to find the percent of female brown bears that are between 100 and 129. So looking at our graph, 100 is right here, and then 129 is at the edge of this bar. So we're interested in these 3 middle bars. That's the weight, those are the ones that weigh between those 2 weights. So what we're going to do for these is we're going to estimate the percents. So for each bar, there's a certain percent when we read it on the table. Each one corresponds to a certain percent. And then we're going to take those percents and we're going to add them. So we're going to add the percent. So we have, for our first bar, because we're starting here, so we have to add these 3 bars. So for these 3 bars, so for our first bar, if we're looking at our percents, each line goes by 5s. So we're in between 20 and 25 here. So if we're estimating, I would say we're at about 23. So we're going to take 23, and then we're going to add the percent for our next bar, and we're just past 40, so we'd say maybe 42. And these, if you vary a little bit, like 1 or 2, like if you said that you were at 24, or if you said that you were at 41, as long as you're close, because this is kind of like an estimation thing, because you're not told exactly what percent it is. So as long as you're close, you're fine. So we've got 23, 42, and then our third bar is at the same height as our first one. So we're going to add another 23. So that's going to give us the total percent that's between 100 and 129. When we add those, we're going to get 88. So 88% are between 100 to 129 kilograms. So 88% of your female brown bears weigh within that range. Now, part B.
Hi, can I send you from
wants to know approximately what percent of female brown bears weigh less than 120 kilograms. So 120 kilograms is this bar right here. So we want to know what percent weigh less than that. So we're going to add all of these bars to the left. So we're going to estimate our percents and then we're going to add them. Now it is kind of hard to see on your graph and on the graph up here, but there is like a little bar over here in the 80 to 89%. There's just a little tiny sliver over there. So we're going to find this bar, this bar, this bar, and that little sliver. So our tall bar we determined was 42 in part A. Then we're going to add the next bar, which we said was 23 in part A. Then we're going to add the 90 to 99, which is right on the 5. And then that little sliver we'll just say is 1. And when we add these up, you should get 71. So that means that 71% are less than 120 kilograms. So 71% of our female brown bears weigh less than 120 kilograms. So that's using a graph that you're provided to find the percents. Examples 2 and 3, we're going to go back and use our normal curve that we were given. So we're going to now interpret off of the normal curve. If you're not given a graph in the problem like we were in the female brown bear one, you want to automatically go to this default curve. This is your standard normal curve. And it will be provided for you on your test, so you don't have to memorize the percentages and all that. But just so you know which curve you want to look at. So for example 2, it says that scores for a certain professional exam are approximately normally distributed with a mean of 650 and a standard deviation of 100. And then part A wants us to see what is the probability that a randomly selected test score is between 450 and 850. So we're given a range, and we're given the mean and the standard deviation. So we have to find where this 450 is on our graph and where the 850 is on our graph. So the first thing that we're going to do, we need to find how many standard deviations, or how many deviations away we are. And then we're going to find percents using the graph. And then we're going to add those percents, just like we did with the brown bears. So the first thing that we need to do is find out how many deviations away we are. So 450, we have to find where 450 is. So we're going to take our mean. This is just like when we were finding standard deviations on Friday. So we have 650, and we're going to subtract our standard deviation, which is 100. And we get 550. So that's one deviation to the left of our mean. But we're looking for 450, so we have to go and take the 550 and subtract 100 again. And that's going to give us our 450. So we're 2 deviations to the left.
deviations or those are dotted lines?
Yes, those are the dotted lines on the graph, which after we find the 850, we'll go to the graph and look at where we actually are. So now we need to find where 850 is. So we're going to take our mean value again, which was 650, and this time we're going to add 100. And that gives us 750. So that's one deviation to the right now. So we're going to do it again like we did on the other side. We're going to take 750 and add 100 again. And that's going to give us our 850. So now we want to look at the curve. So I'm going to move this down just so I can get the curve in here. So we said that we are 2 deviations to the left. So our mean is in the middle here, is this middle dotted line. This first dotted line to the left would be your 550. And then 2 deviations away, we're at 450. So we are right here for 450. Now the 850, we're going to go back to our mean. This first deviation to the right is 750. And then the second deviation is your 850. So we're right here. And we want to find, in the problem it says that we...
Where do you see 850? Like, I don't see like where you're seeing it. I just see like the decimal.
You're not seeing it.
Oh, on the, you mean on the chart here?
Yeah.
The 850 and stuff aren't on your chart. You would have to label your chart. So like, for our problem, our mean is 650. So our middle number right here, the mean, would be 650. And then when you add 100 at 1 standard deviation, you're at 750. And if you add 2 standard deviations, so you're adding 100 to this again, you're at 850. And then the same thing to the left. You're subtracting 100, so you're at 550. And then you're subtracting 100 again from 550, so you're at 450.
So you'd be at like the 95% now?
So you have 95% like included. So we want to find the probability of selecting a score between 450 and 850. So just like with the brown bears, we're going to add up our percentages. But in this case, we're given decimals. And then we'll convert it to a percentage. So we're going to add all of these percentages, or all of those decimals. Because we're finding probability of 450 being less than or equal to whatever value we end up picking, because we can pick any value. And then that would be less than or equal to 850. So we write our probability as a range, because we can find any score within that range. So then, like I said, we're going to add these decimals. So we have 0.1359, and then we add 0.3413 plus 0.3413, and then plus our last one is 0.1359. And what this is showing you is it's showing you the percentage that's in each like deviation away. So this is a little over 34% is included in this deviation, a little over 34% is included in this deviation. This is a little over 13.5, and so on. So when we add up these decimals, we're going to get 0.9544. And then converting that to a percentage, you're gonna multiply by 100 or move the decimal 2 places to the right. And that gives us a 95.44%, which, like Trevor said, would be expected because it says that approximately 95% of our area is within that section. So then for part B, it wants to know, out of 1,000 randomly selected test scores, how many would we expect to be between 450 and 850? So we have 1,000 randomly selected tests, and we want to know how many are in that range that we just found in part A.
So is 1,000 the mean? Oh, no.
So we're going to take 1,000, and we're going to multiply, not by our percentage, because that would give you a really large number. You're going to multiply by your decimal, because remember, when you're finding a part of the 1,000, you want to multiply by the decimal. So we're going to multiply by 0.9544. And that'll give us 95.44% of the 1,000. So we're going to get 954.4. But it wants to know how many tests we would expect. You can't have 0.4 of a test. So we're going to round to a whole number. And when we round to a whole number, we get that it should be approximately 954. So out of those 1,000 tests, approximately 954 should score within 450 and 850. They should score within that range. And then example 3. Example 3 is very similar to example 2, except now we have a different mean and a different standard deviation, and we're talking about something different. So it says that the heights of adult American males are approximately normally distributed, with a mean of 69.5 inches and a standard deviation of 2.5 inches. What percent of adult American males are between 67 inches and 74.5 inches tall? So, like we did in example 2, we want to find how far away 67 inches and 74.5 inches are from our mean. So our new mean is 69.5 and our standard deviation is 2.5. So we're going to take 69.5 and we're going to subtract 2.5 because we want to find this lower number. When we subtract 2.5, we get 67. So 67 is one deviation to the left of our mean. And then we need to find our larger number. So we're going to take our mean again was 69.5. And we're going to add our standard deviation, which is 2.5. That's going to give us 72. So that's one deviation away from the mean on the right-hand side. But we're looking for 74.5. So we need to take our 72 and add 2.5 again. And that's going to give us our 74.5. So we're one deviation to the left, two deviations to the right. So if we're looking at our curve, our new mean is 69.5. And if you need to draw this curve, draw the curve. Like I say, one will be provided for you, but it's good to know. You need to be very comfortable with this curve. So your mean is at 69.5. So we said that 67 was our first deviation away, which is over here. So this is 67. And then we said that 74.5 was 2 deviations away. So this was 72, this is 74.5. So we want to know the percent that's between the 67 and the 74.5. So we want from here to here. So we need to find this, this, and this. Those 3 areas are the 3 areas that we're interested in. Those are between our 2 numbers. So again, writing this as a range, we want percent that is between 67 and 74.5. So you're looking for those heights that are in between that range. So again, we're going to take our decimals and add them. So for this area, we have 0.3413, and then we have 0.3413 again. And then our last section, we have 0.1359. So we're going to add those up, and you should get 0.8185, which will give you 81.85%. So 81.85% of adult American males are between 67 inches and 74.5 inches tall. And then our last problem, part B, says in a group of 2,000 adult American males, about how many would you expect to be taller than 6 feet? So the first thing that we need to do for part B is notice that we're given 6 feet. In our original problem, we're given everything in inches. So we need to change that 6 feet into inches. So we know that there are 12 inches in a foot. So we're going to take 12 times 6. So this is actually 72 inches. So we want to know all of the adult American males that are taller than 72 inches. So we're looking at probability of having someone taller than 72 inches. So we found that in part A, one deviation to the right, so right here, was 72 inches. So we want to know all the ones that are taller than 72 inches. So that's going to be everything else to the right. Now for this one, we can't just add these percentages, the 0.1359 and the 0.0214, because there is a little bit that continues past your third deviation. Remember, we said that in between the 3 deviations, that was only 99% of your information. So there is that little bit that's past there. So what we're going to do is we know that at the mean, so at our middle point, to the right, from our middle point to the right, or our middle point to the left, we know that that contains 50% of our information. So 50% of our information is to the right of the mean, 50% of our information is to the left. So we're going to use that fact to find this percentage. Because we're interested in this whole side, except for this part. So the part to the right. Oops. So we don't want to include that part, this section. We want everything else except for that section. So what we're going to do is we're going to take 0.5, which is 50% written as a decimal. We're going to take that 50% and we're going to subtract the part that we don't want. So we're going to subtract 0.3413. That's our unwanted part. So when we subtract that, we get 0.1587. So that's 15.87%. So we found the percentage that's greater than 72 inches. However, we are told in the problem that we're given a group of 2,000 adult American males, and we want to know how many are going to be taller than 6 feet. So like we did in part B for example 2, we're going to take 2,000 and we're going to multiply by the decimal that we just found. So by that 0.1587. When we multiply that out, you're going to get 317.4. Now again, we want to know the total number of adult males. So we want to get a whole number answer because you can't have 0.4 of a person. So we're going to round this answer again. So you're going to get approximately 317. So approximately 317 adult American males are over 6 feet tall out of your 2,000. So you could expect 317 to be taller than 6 feet tall.
Do you want them to round down? If it was
No.
317.6?
No. So for these, you're going to use your normal rounding rules. So if that decimal, so if it was like 0.5 or above, you would round up. So it would be 318. But where this is a 4 or anything lower, you would round down. So that makes it the 317. So make sure you know your rounding rules. The last page, front and back, is your homework. It follows along pretty much with the examples. The first 3 are like the brown bear problem, where you're interpreting the graph that they give you. And then all the rest are using the standard normal curve. So that curve, so this curve, using this curve to find those answers. So make sure you're comfortable with this.